Hello everybody, and thanks for watching today's video. I have to apologize, I have a bit of sniffles, so I'm going to try to keep that sniffling to a minimum, but we'll see what happens. Anyway, we have an induction proof here. Our objective is to prove that the sum of this series can be calculated by using the simple formula half of n times the quantity 3n plus 1. It took me a while to catch on to this particular truth because of the fact that the numbers in my series are dependent on the value of n. That usually doesn't happen, so I have to sort of spend some time understanding this before I try to prove it. It would be silly to try to prove something that didn't make sense to me. So I substitute in n for 1 and verify that the formula holds. And it's a little tricky because when n equals 1, the first term, n plus 1, is equal to the last term, 2 times n, which means when n equals 1, there's only a one-term series, and so the sum is 2. And that holds for the formula, so that's good. When n equals 2, we start at 3, and then we go to 2 plus 2, which is 4, which is the same as 2n, so we stop there with a two-term series. And that also holds with the formula. Finally, when we get to n equals 3, and I'll even say we can jump ahead to n equals 4, sorry, I was just off track for a second here. We can see that every time I change the value of n, the first term in my series is going to change. It's going to be up one higher. So we're not starting always at the same value for every series and just adding an extra term, which is different from the other series that we studied prior. So that's the first difference I noticed. And the second thing I noticed is that each series has n number of terms. n equals 3 had a 3-term series, and n equals 4 had a 4-term series. And another observation that I didn't write down was that when n equals 2, the last term was 4, and when n equals 3, we added 5 and 6. When n equals 3, the last term was 6. When n equals 4, we added 7 and 8. So my series is always going to have the last two numbers be 2 higher than the highest number of the previous highest number. I know it's a mouthful, but you get what I'm saying, I hope. Alright, so now at least I understand what's going on. I have to think a little bit differently about my inductive process here. But the first part is rudimentary as always, allow n equal to 1, and I already did the busy work there when I was trying to understand, so I just copied and pasted. The statement holds true for n equals 1, and then we assume that when n equals k, the sum of k plus 1 plus k plus 2 and so on, all the way up to 2k, should be k over 2 times 3k plus 1. I'm going to assume that's true, and what I need to do is to show that when n equals k plus 1, that we get 1/2 k plus 1 instead of n, 3 times k plus 1 instead of n plus 1. So this is the expression I need to shoot for, and the only thing I'm allowed to do is to actually use this series as it's defined. So k plus 1 is my first, k plus 1 plus 1, k plus 1 plus 2, k plus 1 plus 3, and so on. And then here's the part about my observations earlier that were really helpful. 2k was the highest value in the previous series, so I'm going to go 2 terms above that. So I got 2k plus 1 and 2k plus 2. These are all the new things. So it extends 2 terms past the previous high, and it also starts off 1 higher than the previous low. So now this is the part where we have to get a little creative. So this is the challenging piece of the puzzle, and that is when I look at all of these, I can see that there's a sum of terms that leads up to 2k, but it's not the same as the one for which I made my assumption earlier. My series is missing the term k plus 1. So I need to add k plus 1 in order to make this match. But whatever I give, I must take away to maintain balance, so I'm going to subtract k plus 1 to keep the balance. All of the stuff under the green bracket, or above the green bracket, is equal to k over 2 times the quantity 3k plus 1 by my assumption. So this is where the induction step is going in. Because of my assumption here, I can take all of the stuff I wrote here and make it that. Plus the 4k minus 1k is 3k, and then the 3 minus 1 is 2. So simplify all this and I get the quadratic expression as seen. Now all I have to do is verify that this expression is equal to that expression. I could do so either by factoring this expression or by foiling this out, and either way I end up with the same truth. So therefore, since the series is true for n equals 1, and the assumption of n equals k leads to, assumption of truth for n equals k leads to the truth for n equals k plus 1, then by the process of mathematical induction, the sum formula holds for all n that are positive integers by the process of mathematical induction. So I hope you found this helpful. Again, the big key to success here is in some inductive proofs, you have a form that looks like your assumption, but you need to make some modifications. And you can stay on the same side of the equal sign, but just give and then take away a missing term, and then you can actually have the expression that you're looking for. That'll come in handy later, so try to keep a note of that. Thanks for watching.